Welcome back to Lecture 5 in our third week of the course, Analysis of a Complex Kind. Today, we'll learn about some properties of analytic functions. So far, we have defined what an analytic function is by looking at what it means to be complex differentiable, and then we looked at some examples, and we defined the exponential function, trigonometric functions, we looked at polynomials, and so forth. Today, we'll look at functions more generally and find some of their properties if we require that they are analytic. Here's the first theorem that we'll talk about today. Suppose f is an analytic function on a domain. Remember what a domain is? That is an open and connected set. So it's all in one piece. And suppose that you have that f prime of c, the derivative of f, is equal to 0 everywhere in D. The theorem says that must imply that f is constant. And this is not all that surprising because we kind of know the one-dimensional analog. If f is a function that's defined on an interval, and it's differentiable, and its derivative is 0 for all x, then f is constant. And the image that we have in mind there is, well, what else could it be? Here's my interval from a to b, and I'm supposed to draw a function, but the derivative is 0. Remember, the derivative, the one-dimensional derivative, meant the slope of the tangent line. So I'm supposed to draw a graph that is nice and in one piece and smooth, and it has a tangent line with a 0 derivative everywhere. So the only way to do that is to draw something constant. It's supposed to be constant. So we'll use this one-dimensional fact and use it to prove the complex fact. Here's the idea of the proof. First, we show that the function f that's analytic and whose derivative is 0 in all of D must be constant in any disk contained in D. So D is your domain, and who knows what it looks like, and then we have a hole, here this is not part of D. This first fact says as soon as you pick a disk that fits inside D, in that disk at least we know that f must have the same value everywhere. And the second part of the proof is then use that we already showed that f must be constant on any disk that we pick, and the fact that D is connected, so it's in one piece, to show that f must be constant throughout D. Now I'll quickly show you how one would write these proofs. Here's the first part of the proof. Suppose we have a disk that fits into D. So here I just drew that disk without actually drawing D. D is some domain that goes somewhere around, we don't really know where it is. But here's this disk that fits into D, and the center we denoted by A, and its radius is R. It's really not important. Pick another point C in this disk, an arbitrary point. We're going to show that f at A and f at C must agree. Because C is an arbitrary point, this will show that f must be constant. It has the value f of A everywhere in this disk. Once you've picked a point C, pick a point B, as in this picture, so that's on the same horizontal line as A, and on the same vertical line as C. So the derivative of f is 0 everywhere in D, and if you write f as u plus ib, then ux, uy, vx, and vy must be 0 in D, because f prime is ux plus I, vx, and the Cauchy-Riemann equations also give us that uy and vy must be 0. So in particular, let's look at the function u, the real part of f, on this line segment here. On that line segment, y doesn't change, the imaginary part doesn't change, only the x coordinate changes. So on this line segment, the function u only depends on x, and y is fixed. And we have that the x derivative is 0. We can therefore look at u as a one-dimensional function here. We fix y, the y value. It only depends on x, and the x derivative is 0. We can therefore use our one-dimensional fact and see that u must be constant on this particular line segment. But that means that u of a must be equal to u of b. Well, then you can do the same kind of arguing on this vertical line segment. Here, the real part is fixed and only the imaginary part varies. So u is now a function of y only on this vertical line segment, but the y derivative is 0. And again, you can conclude from the one-dimensional fact that u of c and u of b must agree with each other. But if u is the same at a, at b, and at c, it must be the same at a and c. So we have u of a is equal to u of c. But c was an arbitrary point in this disk, and therefore u is a constant function on this disk. And you can see that similarly, you could have made the same argument for v, the imaginary part of f, and also gotten that v must be constant on this disk. So that shows the first part of the proof of our theorem. Here's the second part. Suppose A and B are now two arbitrary points in our domain D. They don't necessarily lie in the same disk. I can't draw a disk large enough around A that fits into D and contains B. That disk would have to contain parts that are not in D. So I can't really use the first part directly to prove that the function must agree at A and B. However, D is connected, and so I can find this nice curve here, connecting A and B within D. I could even make that from line segments if I wanted to. By the previous step, f is constant in a disk around A. If I draw a disk that's small enough so it fits into D, f is constant in this green disk that I drew here. But now let's look at this neighboring orange disk. That's another disk, and in any disk, f is constant, so it's also constant on this disk. But these two disks overlap, the green and the orange disks, they overlap on this piece here. F is constant on the green disk, so say f is equal to 1 plus I on that green disk. F is also constant on the orange disk, so let's say f is equal to 2 there. But on this blue portion where they overlap, those two constants are going to have to agree. So the constant must be the same for the green disk and the orange disk. So f is now constant on the union of the green and the orange disk. But I can continue on like that. Look at the next disk that overlaps with the orange disk. F is going to be constant on that next disk, but it overlaps with the orange disk, so it has to be the same constant. And so forth. I continue on in this matter until I reach a disk that contains B. And altogether I can conclude that f of A and f of B must agree with each other. And therefore, f is constant in all of D. Now this theorem, as simple as it is, together with the Cauchy-Riemann equations, has very strong consequences. Here are some examples. Suppose again f is written as u plus ib, and it's an analytic function in a domain, open connected set. And suppose furthermore that the real part is constant. This then implies that f must be constant in D. You cannot find an analytic function whose real part is constant and whose imaginary part varies. As soon as the real part is constant, everything is constant. How would you prove that? Well, u being constant in D implies that the x and the y derivatives are 0 in D, because u is constant. Since f is analytic, it satisfies the Cauchy-Riemann equations, and they imply that ux is equal to vy. Since ux is 0, vy must be 0. uy is equal to minus vx, but uy is 0, so vx is also equal to 0. So vx and vy are also equal to 0. But now, remember, for an analytic function, f prime is equal to ux plus I vx. And we just showed that ux and vx are both equal to 0, and that makes f prime equal to 0. But the previous theorem shows that f then must be constant. So the Cauchy-Riemann equations strongly correlate the real part and the imaginary part of an analytic function with each other. They're not independent. You cannot pick u to be constant and then have any choice on what to do with v. Once you pick u to be constant, v has no more choices left. Similarly, if f is an analytic function in a domain and v is constant, so the imaginary part is constant, then f must be constant in D as well. Also, if f is analytic in a domain D again, and its absolute value is constant, remember the absolute value of f, actually the square of the absolute value of f of z can be found by taking the real part squared plus the imaginary part squared. So if the absolute value of f is constant, then this 2 implies that f itself must be constant. So not even the absolute value can be constant. So let me show you why. Here again the assumptions. F is an analytic function in the domain, and its absolute value is constant. If the absolute value is constant, then the square of the absolute value also can vary. So therefore there must exist some constant c such that u squared of z plus v squared of z is equal to c no matter what z you plug in right here. That's what it means to be constant. Well, there's two choices. The c here can be equal to 0, or can not be equal to 0. If it is equal to 0, then this equation actually reads u squared plus v squared is equal to 0. But u and v are real valued functions. The square of two real numbers is equal to 0 if and only if these two real numbers are themselves equal to 0. So this would mean that f had to equal to 0, and that's certainly constant. And so in this case, we're done with the proof because we have shown that f is constant equal to 0, in fact. If, on the other hand, this constant c is non-zero, because u and v are real numbers and we're adding the squares, the result has to be something positive. So c is in fact positive. Now comes the trick. We're going to look at this equation right here, and we're going to take partial derivatives with respect to x and with respect to y. How do you find the derivative with respect to x of u squared of z? U squared of z is the composition of two functions. It's the function u of z composed with a function that squares. The derivative of that by the chain rule is 2 times u of z, and then times the derivative of u itself, which is ux, because we're taking the derivative with respect to x. So the derivative of u squared of z with respect to x is 2ux. Similarly, the derivative of v squared of z with respect to x is 2vx. And on the right-hand side, the derivative of a constant is 0. So this is the equation that results when we take a derivative with respect to x of this equation up here. Over here, you see what happens when we take a derivative with respect to y. You get 2uuy plus 2vvy is equal to 0. Now let's use the Cauchy-Riemann equations. Remember that vx is equal to negative uy, and we're going to substitute this fact in this first equation. So instead of vx, we'll write negative uy. And in the second equation, we're going to use that ux is equal to vy, and substitute vy with ux. And we'll also divide by 2 here. What we end up with is ux minus vuy is equal to 0, and uuy plus vux is equal to 0. Now let's multiply this equation on the left by u. Well, then u times u squared times ux minus uvuy is still equal to 0. And on the right, we multiply by the function v. uvuy plus v squared ux is equal to 0. By the way, I've been omitting the parameters z with parameter x and y because the equations would otherwise just look more complicated. Every single one of these equations is really u squared of x comma y plus ux of x comma y minus u of x comma y times v of x comma y times uy of x comma y. But that would make everything just look more complicated. So these are the two equations that we were left with on the last page. Now we're going to add these two equations. What happens when I add these two equations to each other? For the first equation, we have a minus uvuy, and in the second equation, we have a plus uvuy. When we add the two left-hand sides to each other, these two will cancel each other out. And all that's left is the first term, u squared ux, and the second term of the second equation plus v squared ux. And the right-hand side 0 plus 0 add up to 0. Here we can factor out the ux, so this reads u squared plus v squared ux is equal to 0. But what is u squared plus v squared? That was constant by our assumption. That's our constant c. So this last equation becomes c times ux is equal to 0. But c is a non-zero number. In fact, we showed it's positive. The product of two numbers can only be 0. One of the two factors is 0, which means ux must be 0 throughout d. You can do a similar calculation by using different substitutions, multiplying with different numbers, and find that uy is also equal to 0 in d. And now using the Cauchy-Riemann equations, once you have that ux and uy are 0 in d, you can find that vx and vy are also 0 in d, and therefore f prime is 0 in d, and we're back to being able to use a theorem which says that f must be constant in d. By the way, d being connected is really important here. Because you could imagine a case where d consists of two open sets, and you can have a function being constant equal to 1 on this set and being constant equal to 2 on this set. And the function overall wouldn't really be constant, it's only constant on these portions. And so that's why d being connected is important to imply that the function is constant throughout. Let's finish with a really strange example. The strange example is the function f that's defined in the whole complex plane by e to the minus 1 over z to the fourth for non-zero z values, and 0 at the origin. Clearly, 1 over z to the fourth is an analytic function. Analytic wherever z is non-zero. So it's analytic in the complex plane minus the origin. The minus sign still makes an analytic function. The exponential function is analytic, so the composition of these two is analytic. So in c minus the origin, clearly this function f is analytic. In fact, one can find u, v, their x and y derivatives and all that, and show that they actually satisfy the Cauchy-Riemann equations everywhere in c. They clearly satisfy them in c minus 0 because we just saw that f is analytic in c minus 0, but they actually satisfy them at the origin as well. And one can in fact show that at the origin ux, uy, vx, and vy are all equal to 0. However, it turns out f is not differentiable at the origin. How is that possible? F satisfies the Cauchy-Riemann equations everywhere in C and is not differentiable? Isn't that a contradiction to some theorem that we had earlier? In fact, f isn't even continuous at the origin. So a function that's not continuous can't be differentiable. Remember, if a function is differentiable, then it's automatically continuous at that point. Since f is not continuous at the origin, I'll show you why. F cannot be differentiable at the origin. So we'll have to solve this mystery in a little bit. So how is this possible? For now, I'm just going to show you why f is not continuous at the origin. So here's the function again. Why is it not continuous? What does continuity mean again? Continuity means that the limit of f of z, in this case as z approaches 0, should be equal to f of 0. That's what continuity would mean. The limit has to exist, and as z goes to 0, that limit has to equal f of 0. So we need to look at what happens as z approaches 0. What happens to f of c? Does the limit exist? And as always, we're going to look at z approaching the origin along some standard ways, along the x-axis, along the y-axis, and so forth. Let's start z approaching the origin along the real axis. So z is of the form x plus I times 0, so no imaginary part. And letting that go to 0 means x is going to go to 0. Then f of z is simply f of x, and that's e to the minus 1 over x to the fourth. As x goes to 0, this denominator here goes to 0. 1 over that goes to infinity, but there's a negative sign in front of it, and so the exponent here goes to negative infinity, and e raised to a number that's going toward negative infinity actually goes to 0. Just remember the exponential function looks like this. And if you plug in numbers that are closer and closer to negative infinity, the exponential function gets very close to 0. So as x approaches the origin along the real axis, f of x goes to 0. All right, so maybe something will happen along the imaginary axis. So let's next consider z approaching the origin along the imaginary axis. That means z is of the form iy, no real part, just iy, and that's going to go to 0, so y goes to 0. What's f of z? What's then f of iy, which is e to the minus 1 over I to the fourth, y to the fourth. But I to the fourth, that's just 1. So it's e to the minus 1 over y to the fourth, and the exact same reasoning that we used before shows that, again, f goes to 0. So f goes to 0 as you approach 0, both along the real and the imaginary axis. So far so good, right? Where's the problem? So far it looks like f is indeed continuous. However, consider z of the form r e to the I pi over 4. So z's going to 0 along a 45-degree angle. What is z to the fourth in that case? Well, it's r to the fourth times e to the I pi over 4 times 4, which is e to the I pi. And what is e to the I pi? E to the I pi is negative 1. So z to the fourth is minus r to the fourth, and that minus sign is what's going to be the cause of all trouble. What's f of z? It's e to the minus 1 over minus r to the fourth, and these two minus signs will cancel each other out. So f of z is now e to the 1 over r to the fourth. But as r goes to 0, 1 over r to the fourth goes to infinity, and there's no negative sign there to rescue us. The exponential function, as you plug in numbers that are bigger and bigger towards plus infinity, goes towards plus infinity, and that is certainly not equal to f of 0. So the limit doesn't even exist, and it certainly doesn't equal f of 0, which shows that the function is not continuous at 0. So with f not being continuous at 0, it's also not differential at 0. So let's go back to the original problem. What happened? U and V satisfy the Cauchy-Riemann equations everywhere in C, yet f is not differential at the origin. How is that possible? Well, this is what our theorem really said. Let f be defined on a domain D. Then f is analytic in D if and only if U and V have continuous first partial derivatives in D that satisfy the Cauchy-Riemann equations. So it's not quite enough just to satisfy the Cauchy-Riemann equations. The partial derivatives have to be continuous. In our strange example, these partial derivatives are not continuous at 0, and so the assumptions of the theorem are simply not satisfied. Even though they seem to satisfy the Cauchy-Riemann equations, that's not enough. They need to be continuous in addition. So that's what went wrong in this example. It's a very subtle example, and most of the time, this won't affect you in the least. Next week, we'll study conformal mappings. Those are analytic functions that are injective, or one-to-one in addition, and they'll have some very special properties that we'll learn about. We'll talk about some examples of conformal mappings, namely the Mobius transformations, that are fascinating in and of themselves. And as a bonus, I'll show you the Riemann mapping theorem, which says the following. Suppose I'm giving you some kind of domain, again, open connected set, but this time I'm not allowing that domain to have a hole. So any domain that's not having a hole, so something like this is not allowed. So the only kind of domains that I'm going to allow are the ones that have no holes. Suppose I'm giving you such a domain, then I can find an analytic function that is one-to-one and onto from this domain, no matter how ugly you drew that, onto the unit disk. And it's going to be a conformal mapping, so it's going to be analytic, one-to-one, injective. I'll explain what that means next week, and onto. So in other words, the Riemann mapping theorem makes it possible to transfer things back and forth between this domain and the unit disk. This is one of the most amazing theorems in complex analysis, and we'll learn about it next week.